Okay, for those of you who are out with COVID, either having the symptoms or being tested positive or just being quarantined because you were around somebody who was. This is for you. I'm going to give you a quick overview of the test that's going to be due by Monday at the beginning of class. So it'll be due Monday at 5:30 p.m. So anyway, let's start with that real quick. So I'm going to run right down the line here with you, kind of what's on the test, but I'm going to try and steer away from the language verbatim, but give you an idea so you can try and get a head start on trying to find answers so that the hour should be plenty of time to get it done. So with that being said, the first one is what happens if the pump's inlet is size too small? We've talked about this many times. What can happen with a pump? What does it lead to? So restricting the inlet size of the pump. It's a true and false question, but you'll need to know what that is. The next question on here has to do with the pump in this diagram. So part of this module is this diagram. You should have a paper copy of it. I would suggest using your paper copy. It's going to be 11 by 17. If you want to open this one up and use a second screen to use this on another screen, so be it, however you want to do it. I don't care. Or you can print it off. Print it off at home, though, it's probably going to be a little smaller. So try and use this one. It's a little easier to read if you got a paper copy. So first thing it's asking is what kind of pump? Now, again, this is a true and false. I'm not going to give it to you that way, but what kind of pump is in this system? So it's right here. If you look closely, this little line with an arrow going up means it's what? We talked about it in our classes relating to symbols. So anytime you have any device in a hydraulic system that has a diagonal angle coming up means it's a variable. So when it's drawn through a pump, it's a variable displacement. There's some magic words right there. It tells you what it is. So again, everything you need for that question is right there. Next question is what kind of a directional control device is attached to the eject cylinder? So the first thing you got to do is find where the eject cylinder is. It's right here. They're all labeled on this drawing. So the eject cylinder is here. What kind of device is that? How many ports? How many positions? Next question I've got for you has to do with the operating pressure of this system. Something we didn't talk about a whole lot in class, but I'll cover it right here. If you've got pressure in a system, it's going to be usually listed near the pump on there. So what pressure do you want to operate your system at? Ignore anything else on the rest of the system. It's going to be down here. Another thing I did not cover in class is variable pumps. So the way that you adjust a variable displacement pump for its maximum flow rating, you have to have the system wide open. So you basically have to have this pump pumping right back into the tank to be able to set your flow, your max flow on that. So that'll be the next question. And wide open is the opposite of deadhead. Valve number 106. Valve number 106 is right, it's even hard for me to read it on the screen here. Give me a second to find it. Sad I can read it better on the paper than I can on the screen up there. 106 is right here. It doesn't look like a 6 here, it looks like a 4, but that's a 6. It's 106 right there. It's that valve. We all know what that is. Next question is, how does the die height cylinder return? That's right here. Notice the diagonal lines coming through here. We talked about what that is, what that means inside of a cylinder. You should be able to get that. Sorry, it's a die height lock cylinder. Next question has to do with the solenoid R on valve 102. Valve 102 is right here. If I energize R, move this over this way, what happens to the cylinder? Does it advance or return? You'll need to know that. Something else we talked about very briefly in the class. Every one of these little loops here, or half loops, they're all over the place in this drawing. Those are hoses. We always connect pumps by hoses. That isolates this whole thing. Represents an assembly. The pump assembly is isolated from the rest of the system. We do that because we don't want to put the vibration through all the steel lines that typically feed all your devices. So, understand that. If fluid pressure, this is a repeat question from the last test that we had. If you have equal pressure on both sides of a motor, is any work being done? You will always have a pressure drop when there's work being done. So if a motor is turning, that is considered work because there's some motion that comes out of it other than just flow. So remember that. So now I get into my notes. Next question on here has to do with the displacement of a die height motor is 50.27 cubic inches per revolution. What's the working pressure at 1500 psi? What kind of torque will it make? So, torque equals pressure in times your displacement divided by 2 pi. The equation's on page 166 in the hydraulic book. Remember how to calculate horsepower, but here's an easy solution. It's horsepower equals gallons per minute times your PSI times 0.007 equals your horsepower. You'll need that. That's on page 24 in your book. Again, that's the hydraulics book. We've got another question here regarding the gas laws. Gas laws, so if you have a pressure in an enclosed tank that is sea level pressure, it's 14.7 psi. Talked about that. If you lower that temperature down, if it's 80 degrees when you put it in, you lower it down, what happens? So you're going to have that. That's this formula down here is P1 times V1 over T1 equals P2 times V2 over T2. The kicker to this is P equals absolute pressure. So absolute pressure is, if it's gauge pressure, it's pressure plus 14.7 psi. Volume can be cubic inches, it can be gallons, it doesn't really matter. It's directly related. T is absolute, so it's your Fahrenheit plus 460 degrees. There's another one on here that's asking about what can happen in a system, what can cause it to overheat. We talked about a lot of different things that will overheat. In this particular case, it's 180 degrees Fahrenheit already, which is about as hot as you want to run hydraulic oil. You don't want to be much over that. So what's some of the things that could cause that? Your pressure's already at 2450 psi and you got a flow rate of 31 gallons per minute. Pretty much gave you that. So think about it. You're going to need to list 2 things that can cause it to overheat based on the information given. Gave away some hints in class here the other night, just about how to draw flow controls. Flow controls are, they have curves. Everybody likes curves. Flow control is like this. Got it around. Check valve in the middle of it. Okay, so with the check valve drawn this way, and I drew it nice and big so you guys can see it, hopefully everything's clear. When your flow is coming this way, it's going to be forced to go this way. When your flow is going this way, it will free flow this way, pushing the ball off the check. This is your adjustable orifice. This is your cylinders here. Metering out. Okay, so it should both be drawn this way. If you have them on a cylinder, you have 2 of them, it's going to come this way. Sorry, I don't want to confuse you. You have another one of these down here. These are both marked as a copy. So you'll need to know that. Which way, if your flow is coming out of here, you're actually controlling the speed of the cylinder on the extent. So that's one of your questions on the test is which direction is it controlling. I'm sure you guys know that, but I'm going to make sure that you do. Next question, it has a diagram and it talks about, I just need to show this to you because I don't think it's right. This valve, this question actually calls for pneumatics. This is actually hydraulics. You can tell by the filled in arrows. This isn't my test, but I'm using it. So credit to whoever wrote the test. This is a pressure regulator. It's drawn to represent a pressure regulator in a pneumatic system. So just remember that is a pressure regulator. Back to my cheats. Next valve has to do 2 potential things could be wrong in a circuit. I know you guys can figure this out. I know there's at least 2. So what could be wrong if the cylinder won't retract? What is the cracking pressure of a relief valve? I know I talked about it in one of my other lectures when we talked about relief valves. So cracking pressure is that point where the valve starts to open. That's the cracking pressure. Here's a question about the volumetric volume of air. What's the final air pressure in the tank? Volume stays the same. Temperature drops. 1,000 cubic feet. What do you got in the end? So that's your gas laws. Okay, the next one has to do with the gripper suction with vacuum. I know I just talked about this in the lecture. So it talks about pressure differential. So your lifting force of a vacuum still equals F equals pressure times area. Force equals pounds. Pressure equals vacuum equals difference in pressure. Area equals inches squared. So let's talk about this difference of pressure. Difference of pressure is at sea level we've got 14.7 psi of absolute pressure. At absolute vacuum or 100% vacuum at 29.92 inches of mercury equals negative 14.7 psi. Or it's negative 14 psi gauge, or 0 psi absolute. So, that being said, if you have absolute or pure vacuum, 100% vacuum, at an 1.5 inch diameter, well, let's use a 2-inch diameter because that's easy to do. So, 2-inch diameter, equals 3.14 inches squared. At pure vacuum is 14.7 psi. That's the differential between absolute pressure at sea level and pure vacuum or 100% vacuum at sea level. That will give you your force of a 2-inch vacuum cup. Now to figure out the difference between inches of mercury and vacuum, you can take your inches of mercury times point, I can't remember what it is, it's 0.51, I think. I had it, hold on a second. Google works wonders. .491. So inches of mercury times 0.491 equals PSIA. I know I gave you guys 2.035, I think. you could divide inches of mercury times 2.035, usually the same number. Either way it works, it's just math in reverse. Anyway, that's that. So with that being said, when atmospheric pressure decreases, we talked about in the lecture, then at Mile High City, Colorado, I believe was the example, that at Denver, your mile high, your air pressure is actually only 11 psi, or the difference between absolute vacuum and, I think it's 11 psi at 4,000 feet above sea level. So if it's 11 psi, you can only make 11 psi of force, which is going to drop that down. So your vacuum generator effectively makes less vacuum at higher elevations, or lower air pressure, or lower atmospheric pressure. So the next question has to do with free air delivery of a compressor. I know we didn't talk a lot about free air delivery. We covered it very briefly in the first chapter of the pneumatics book, the second chapter of the pneumatics book. Free air delivery is the amount of air that a compressor needs. Free air delivery is also based on the gas laws. Let's throw it back up there again. Pressure of 1 times volume of 1, or over the temperature. So if your temperatures are the same, you can basically wipe those out. It doesn't really matter. It doesn't mean nothing. So P times V equals P times V, or P1 times V1 equals P2 times V2. If your temperature is the same, it should come out to be the same number. Because you're going to take this, multiply it each way to get rid of that. So, that being said, I would put your temperature in there as just pull a preliminary number just to make sure it works. But your incoming pressure, or I'm sorry, the volume. Volume is what really matters when you're looking at your free air delivery. So free air delivery is CFM, cubic feet per minute. Right? So cubic feet per minute is still cubic feet per minute. That's a volume over time. The time doesn't change, so that can be wiped out. So this still works for your free air delivery. So if your temperature changes and drops, it becomes colder, you fit more air in the same amount of area that you do than you do warm air. So warm air will have higher pressure, but cold air wants to shrink down, so it takes a smaller area to have the same amount of air molecules. So your free air delivery, if something's colder, your intake is colder than what you were taking, it requires less free air. So your free air is colder, it will require less free air. Hope that makes sense. If your outside incoming air is warmer, it's going to increase your free air delivery demand to make the same pressure and temperature on the exhaust on the outgoing side. That works for compressors. You can also use compression ratio. Your compression ratio works only if your air temperature stays the same to figure out free air delivery. So if your incoming air is the same as your outgoing air, if they're both 70 or 80 degrees or 90 degrees, incoming and outside air, you can just use a straight compression ratio. Compression ratio, if you remember, is pressure gauge times, sorry, plus pressure atmospheric over pressure atmospheric. At sea level, atmospheric is 14.7. So if you had 80 psi, your compressor, just say your compressor is making 80 psi, it's going to be 94.7 over 14.7 equals your compression ratio. Hopefully that makes sense. If you have another question on your test in regards to your compression ratio. And one more about free air delivery. So I've covered everything on the test. I hope that helps. I hope that helps better prepare you for it. All this information is available in your books. The compression ratio, I didn't write down the numbers. Gas laws is on page 27 in your book. Compression ratio, I can find that out very quickly. That was at the beginning as well. It was in chapter 2. Compression ratio, and we're looking at it's on page 32 in the pneumatics book, the bottom of the page, page 32. So with that being said, I'm going to cut this one off. I'm going to just send this one to you guys. Hopefully I can just send it to you via email. If not, it'll be posted somewhere and I'll send you a link.